When we talk about Max Planck and his idea that energy is emitted in small packets called quanta, we are actually talking about one of the most important intellectual breakthroughs in the history of human science. This idea did not simply adjust the course of physics. It shattered the old world, opened the gateway to a completely new scientific era, and set into motion everything we now know as quantum theory. But to understand why Planck's idea was so revolutionary, we need to go back to the late 1800s, a time when scientists believed they had almost completely explained the universe using classical physics. During this period, physics seemed nearly complete. Newton's laws explained motion, Maxwell's equations described light as electromagnetic waves, and thermodynamics connected heat, energy, and matter. Many scientists confidently declared that all major discoveries had already been made, yet beneath this confidence was a growing confusion. Certain experimental observations simply did not match classical predictions. One of the most annoying and persistent of these problems involved something called Blackbody radiation, the light and energy emitted by objects when they are heated. No matter how many adjustments scientists made to classical equations, they failed to accurately describe the intensity of radiation at different wavelengths. Some predictions even suggested that an object should emit infinite energy at high frequencies, a ridiculous idea nicknamed the ultraviolet catastrophe. It was into this chaotic scientific puzzle that Max Planck stepped. Planck was a highly precise thinker and a deeply mathematical physicist. His goal was not to destroy classical physics, but to preserve its harmony. However, as he tried to solve the Blackbody radiation problem, he realized something alarming. Classical physics simply could not match the experimental data. It wasn't a matter of adjusting a constant or refining an equation. Something deeper was wrong. Planck spent years designing and analyzing experiments and equations, but classical theory stubbornly refused to yield the correct answer. In 1900, after endless frustration, Planck made a desperate and brilliantly creative decision. He introduced a mathematical trick, not because he believed it was physically true, but because it worked. Instead of assuming that energy was emitted continuously, he assumed that energy was emitted in discrete chunks, or packets, that were proportional to the frequency of the radiation. He represented this relationship with the equation E equals h nu E equals h backslash nu E equals h nu, where E is the energy of a packet, nu backslash none, U nu is the frequency of light, and HHH is a constant that came to be known as Planck's constant. At the time, this was a shocking proposal. Classical physics assumed that energy behaved like a smooth, flowing river. Planck's idea suggested that energy behaved more like grains of sand, tiny pieces that cannot be broken down endlessly. These indivisible energy packets were later called quanta, and their existence implied that nature was fundamentally granular at microscopic scales. This idea seemed absurd to most scientists. Even Planck himself did not fully believe in the physical reality of quanta at first. Yet, mathematically, the idea worked perfectly. It explained the Blackbody spectrum. It eliminated the ultraviolet catastrophe. It matched real-world measurements in a way classical physics never could. The introduction of quantized energy represented a dramatic shift in our understanding of the universe. Before this idea, scientists believed that physical quantities such as energy, light, and heat changed smoothly and continuously. But Planck's discovery implied that nature behaves differently at very small scales. Instead of continuous waves, energy might be fundamentally discrete, jumping from one level to another without passing through intermediate states. This concept challenged centuries of scientific belief and forced physicists to reconsider the most basic assumptions about reality. To appreciate how groundbreaking this was, imagine a dimmer switch for a light. Classical physics assumed that the brightness could be adjusted smoothly, increasing or decreasing with infinite precision. Planck's theory said that the brightness can only change in very specific steps, like climbing a staircase rather than moving up a ramp. These steps were incredibly small, far beyond human perception, which is why classical physics seemed correct at everyday scales. But at the microscopic level, these energy steps mattered enormously. As Planck explored his formula further, he realized that he had not merely patched a gap in classical theory. He had opened a door to an entirely new understanding of energy itself. That door led directly to later breakthroughs such as Einstein's explanation of the photoelectric effect, Bohr's atomic model, Schrödinger's wave equations, and Heisenberg's uncertainty principle. What makes Planck's idea so astonishing is that it emerged from sheer necessity. He was not seeking to overturn physics. He was trying to explain one absurd experimental problem. Yet this mathematical trick would go on to become the foundation of quantum theory, influencing nearly every branch of modern science and engineering. Planck's constant, once introduced simply to make an equation fit the data, became the key that unlocked the atomic world. To understand the importance of this idea further, we need to explore why continuous energy failed and why quantized energy succeeded. Classical theories predicted that an object radiating heat would emit energy at all frequencies equally. This led to the absurd prediction that at extremely high frequencies, such as ultraviolet light, the energy output would become infinite. No object behaves that way in reality. Instead, the radiation curve rises, peaks, and then falls, matching the shape that Planck's formula derived. Planck's insight came from treating atoms and molecules not as tiny mechanical oscillators with a continuous range of energies, but as oscillators that could only possess certain discrete energy levels. When these oscillators jumped between levels, they absorbed or emitted energy in fixed-sized quanta. This idea, though shocking, matched what experiments were telling scientists. Planck's constant, the mysterious number that connected energy and frequency, became a window into a hidden world governed by rules entirely different from those of everyday life. The constant is extremely small, approximately 6 126 times 10 minus 3, 146. 626 backslash times 10 minus 34 6. 626 times 10 minus 34 joule seconds, which explains why quantization is invisible in our daily experiences. But at atomic scales, this tiny constant becomes enormously important. It shapes the behavior of electrons in atoms, the emission of light, the stability of matter, and even the structure of the universe. Although Planck initially resisted the idea that quanta were physically real, he eventually accepted that his discovery carried far deeper meaning than he had first imagined. In a way, his discomfort was understandable. The notion that energy comes in packets challenged everything physicists believed about waves, light, and matter. Energy had always been thought of as something smooth and infinitely divisible, yet here was a formula implying the exact opposite. Once Planck's idea was published, it began to inspire other scientists to take quantization seriously. Albert Einstein was the first to boldly declare that Planck's quanta were not just mathematical tricks, but real physical entities. Einstein used the concept to explain the photoelectric effect, demonstrating that light behaves like a stream of particles, each containing a quantum of energy. This work earned Einstein the Nobel Prize, and strengthened the foundations of quantum theory. But everything began with Planck's first step, recognizing that continuous energy did not fit nature and daring to propose a discrete alternative. His idea changed not only physics, but philosophy. It transformed how we think about the universe at the most fundamental level. It led to quantum mechanics, which revealed that particles behave like waves and waves behave like particles, that energy jumps in sudden transitions, and that uncertainty is built into the fabric of reality. Planck's discovery also laid the groundwork for technologies that define the modern world. Everything from lasers and LED lights to computer chips and medical imaging depends on quantum principles. Though Planck never imagined the practical outcomes of his idea, the ripples of his discovery continue to shape human life. To fully grasp the magnitude of this breakthrough, consider this. Before Planck, the world was viewed as a precise, predictable machine. After Planck, it became clear that at its deepest level, reality is granular, probabilistic, and governed by strange rules unlike anything we experience in daily life. Planck did not just solve a physics puzzle. He initiated a revolution in human thought, opening a door to a realm where particles can exist in multiple states, where objects can tunnel through barriers, and where uncertainty rules the microscopic world. All of this began with one simple but radical idea. Energy is not continuous. It comes in tiny, indivisible packets called quanta. And with that idea, the universe was changed forever. Continuing from the previous explanation, the story of Planck's introduction of energy quanta becomes even more fascinating when we explore what happened after the initial shock wave moved through the scientific community. The idea that energy is emitted in tiny packets did not simply solve a theoretical problem. It began reshaping every corner of physics. Many scientists of the time were deeply uncomfortable with this proposal, not because it lacked mathematical power, but because it challenged the long-standing belief that nature operates smoothly and continuously. This discomfort is what makes the next part of the story especially important. How Planck's idea spread, evolved, and ultimately became the foundation of the modern understanding of the microscopic world. In the early 1900s, classical physics was still so deeply respected that most scientists found it difficult to accept anything that contradicted its principles. Even Planck believed that classical science was fundamentally correct, and that his formula was merely a temporary solution. However, a truly transformative idea has a life of its own. Once released into the scientific world, it attracts new thinkers and new perspectives. This is exactly what happened with the concept of energy quanta. The first major figure to take Planck's discovery seriously was Albert Einstein, who immediately recognized that the idea had much deeper implications than Planck initially realized. Einstein argued that the quantization of energy was not just a property of atomic oscillators. It was a property of light itself. Einstein proposed that light behaves not only as a wave, but also as a stream of particles, each carrying a quantum of energy equal to Planck's formula. This was an even more radical extension of Planck's work, because it implied that something as familiar as light had a dual nature, wave, like and particle, like at the same time. Einstein used this concept to explain the photoelectric effect, where shining light onto a metal surface ejects electrons. Classical physics predicted that increasing the brightness of light should increase the energy of the ejected electrons, but experiments showed that only the frequency of the light mattered, not the intensity. This confusing behavior made no sense unless energy was packaged into discrete quanta. When Einstein applied Planck's equation to the problem, everything suddenly made sense. The acceptance of this idea did not happen immediately. Many physicists resisted the notion that light could behave like particles, because waves and particles were considered fundamentally different. But as more experiments confirmed the predictions of quantum theory, the scientific community had no choice but to rethink its assumptions. Planck's introduction of quanta became the seed from which a new physics emerged. Instead of trying to force classical theories to fit the new data, scientists began developing an entirely new framework built around the concept of quantization. One major consequence of this shift was the development of the quantum model of the atom. Before Planck's idea, scientists struggled to understand why electrons did not collapse into the nucleus or why atoms emitted light at only specific wavelengths. Classical physics could not explain the stability of atoms. But once energy quantization was accepted, Niels Bohr used the concept to propose that electrons occupy fixed energy levels and can only jump between these levels by absorbing or emitting quanta of energy. This idea explained atomic spectra perfectly and formed the foundation of early quantum mechanics. The discrete lines observed in the emission spectra of hydrogen were no longer mysterious, they were evidence of quantized transitions. Planck's contribution thus became central not only to radiation theory, but also to the understanding of atomic structure. His constant appeared everywhere in the emerging equations of quantum mechanics. As scientific thought advanced, two major interpretations of quantum behavior emerged: the wave mechanics of Erwin Schrödinger and the matrix mechanics of Werner Heisenberg. These approaches looked very different but ultimately described the same underlying reality: a universe where energy levels, particle positions, and even time evolution are influenced by Planck's constant. The presence of Planck's constant in these equations is not an accident. It is a reminder that quantization lies at the heart of the microscopic world. Every equation of quantum physics carries Planck's constant as a marker of where classical theory breaks down. Without the concept of quanta, none of this would exist. It is astounding to realize that the entire mathematical structure of quantum mechanics grows from the seed that Planck planted in 1900. His small modification to solve Blackbody radiation became the foundation of a scientific revolution. Another important development following Planck's discovery was the realization that quantization is not limited to energy. Over time, physicists found that properties such as angular momentum, spin, and even the vibrational modes of molecules are quantized. This meant that the universe is much more discrete at the microscopic level than anyone had previously believed. What appeared to be continuous in everyday life turned out to be composed of countless tiny steps. These steps are so small that they blend together at the macroscopic scale, creating the illusion of continuity. This is why classical physics seems to work well in daily life, but breaks down when dealing with atoms, electrons, or photons. The idea of quantization also led to new philosophical questions. If energy exists only in discrete steps, what does that say about the nature of reality? Does the universe operate like a digital system rather than an analog one? Are space and time themselves quantized at some deeper level? These questions continue to inspire modern theoretical physics, including quantum field theory, string theory, and attempts to unify quantum mechanics with general relativity. In every one of these theories, Planck's constant remains a key player, defining the scale at which quantum effects become significant. As quantum theory grew, it became clear that Planck's discovery had implications far beyond basic science. It sparked a technological revolution. Lasers, for example, rely on the quantized transitions of electrons. The stability of atoms, and therefore the stability of all matter, depends on quantum principles. The entire semiconductor industry, including transistors and microchips, is built on quantum physics. Without quantization, computers, smartphones, LED lights, GPS systems, magnetic resonance imaging, and countless other technologies would not exist. When looking at this massive impact, one might wonder if Planck knew how important his idea would become. He did not. In fact, he often described his discovery as an act of desperation, made only because classical physics could not solve the Blackbody problem. But history has shown that breakthroughs often come from moments when conventional thinking reaches its limits. Planck was courageous enough to go beyond those limits, even when he did not fully understand where his idea would lead. His work teaches a powerful lesson about science. Progress sometimes requires letting go of deeply held assumptions. Planck dared to question the continuity of energy, a concept that had stood unchallenged for centuries. His willingness to explore a new idea, even when it seemed strange or mathematically inconvenient, opened the door to some of humanity's greatest scientific achievements. The story of energy quanta also shows the importance of experimental evidence. Planck did not invent the concept because he wanted to revolutionize physics. He introduced it because experiments demanded an explanation. Data had to take priority over established beliefs. This scientific humility, combined with intellectual bravery, is what allowed Planck to see the truth hidden in the Blackbody radiation curve. As time passed, the acceptance of quantum theory transformed physics into a field rich with possibilities. What had once been a rigid, deterministic view of the universe was replaced by a more flexible and probabilistic one. Particles could be both waves and particles at the same time. Energy could appear in packets. Systems could exist in multiple states simultaneously. At the heart of all this strangeness lies the small but powerful constant that Planck introduced more than a century ago. Today, Planck's discovery continues to influence cutting-edge research. Quantum computing, for example, uses the principles of superposition and entanglement, both of which arise from quantization. Quantum cryptography, quantum sensing, and quantum communication all depend on the same fundamental idea. From the tiniest particles to some of the biggest technological innovations, the impact of Planck's insight stretches across disciplines and across generations. Ultimately, the introduction of energy quanta is not just a scientific milestone. It is a reminder of how a single idea can reshape human understanding. Planck's proposal changed the meaning of energy, light, and matter. It introduced the atomic world in a way no scientist before him had imagined. It shattered the illusion of continuity and revealed a deeper structure in nature. It laid the foundation for a revolution that still shapes our world today. The journey from Planck's formula to modern quantum physics is a story of creativity, persistence, and the courage to think differently. It shows how the smallest concept, like the smallest quantum, can have the biggest impact changing science, technology, and the way we see the universe. The Blackbody radiation problem is one of the most important scientific puzzles ever solved, not because it involved dramatic experiments or spectacular phenomena, but because it quietly exposed the limits of classical physics and forced scientists into a completely new era of thought. Max Planck's discovery solved this perplexing problem in a way no one had expected, and in doing so, he laid the first stone of quantum theory. Understanding why his discovery was revolutionary requires an exploration of what Blackbody radiation is, why it troubled scientists, and how Planck's unusual solution finally resolved it. To begin with, imagine heating a piece of iron. As it becomes hotter, it slowly glows red, then orange, and eventually white as the temperature rises. This glow is not simply a color change. It is radiation emitted by the object due to its temperature. Every object emits radiation when heated, whether it is a star shining in space or a stove coil glowing in a kitchen. Scientists call any object that absorbs and emits radiation perfectly a blackbody. Although no perfect blackbody exists in nature, many objects approximate the behavior closely enough to study the underlying principles. In the late 1800s, physicists attempted to describe this emitted radiation quantitatively. They wanted a mathematical formula that could predict how much light of each wavelength a heated object would emit at a given temperature. This sounds simple, but it proved to be a monumental challenge. The challenge came from the fact that classical physics, based on the laws of electromagnetism and thermodynamics, made predictions that were disastrously wrong in certain regions of the light spectrum. Experiments showed that at low frequencies like infrared, blackbodies emitted large amounts of energy. This matched classical expectations, but at high frequencies like ultraviolet, the emitted energy dropped sharply. Classical theories, however, predicted something dramatically different. According to the classical Reimagined law, the energy should increase without limit as the frequency increases. This implied that a heated object should emit infinite energy at high frequencies, which was physically impossible. This absurd prediction became known as the ultraviolet catastrophe, because it suggested that everyday objects would release deadly amounts of ultraviolet light, which clearly did not happen. The ultraviolet catastrophe was more than a theoretical mistake. It was a sign that something fundamental was wrong with classical physics. The laws that worked so well for planetary motion, mechanical systems, and electromagnetism failed miserably when applied to thermal radiation. No matter how scientists modified the equations, they could not produce a curve that matched the experimental results. The problem became a significant embarrassment in the scientific world. If classical physics could not describe such a simple, universal phenomenon, then how reliable was it? For years, physicists attempted patchwork solutions. Some proposed adjusting constants, others revisited the assumptions of wave theory, but none succeeded. The mismatch between classical predictions and experimental data persisted. Even the greatest physicists of the time admitted defeat. It was at this moment of frustration that Max Planck entered the scene. Planck was not an experimentalist. He was a theorist who excelled at mathematical reasoning. His goal was straightforward: derive a formula that matched the emission spectrum of a blackbody at all frequencies. Planck began by studying the existing experimental data carefully, trying to understand the underlying pattern. He realized that classical physics could describe low-frequency radiation well, and that Wilhelm Wien's formula handled high-frequency radiation accurately, but neither theory worked across the entire spectrum. Planck wanted a single unified formula that explained everything. At first, he tried to derive the correct formula using classical assumptions. He treated atoms in the blackbody as tiny oscillators that absorbed and emitted energy continuously. But this approach failed. The calculations always produced curves that deviated from experimental observation. After months of struggle, Planck took a step that changed history. He abandoned the continuous energy assumption that had been sacred in classical physics. Instead, he proposed that the oscillators could only possess discrete amounts of energy. In other words, energy was not a smooth, infinitely divisible quantity. It came in tiny packets, whose size depended on the frequency of radiation. This idea was radical because it violated centuries of scientific thinking. Classical physics treated energy like water flowing from a faucet, capable of being divided endlessly. Planck's proposal treated energy like coins, discrete units that could not be subdivided arbitrarily. He did not propose this idea because he believed it reflected physical reality. Instead, he introduced it reluctantly as a mathematical trick that made the equations work. But this trick worked astonishingly well. The moment he applied it, he derived a formula that matched experimental Blackbody curves perfectly across all wavelengths. Planck's formula successfully eliminated the ultraviolet catastrophe. It predicted that high-frequency radiation would not cause an infinite increase in emitted energy. Instead, the energy would drop off smoothly, exactly as experiments showed. This was the first time anyone had produced an equation that accurately modeled Blackbody radiation from low frequencies to high frequencies. It was a triumph so profound that it shocked the entire scientific community. One of the key components of Planck's formula was a new fundamental constant, which later became known as Planck's constant, denoted h. This constant represents the size of the energy quanta. Its value, extremely small, showed why quantization is invisible in everyday life. At macroscopic scales, energy appears continuous, but at microscopic scales, Planck's constant reveals a granular structure. By introducing this constant, Planck effectively introduced the first quantum of the scientific world. Planck's breakthrough was not welcomed easily. Many physicists found the idea of quantized energy uncomfortable and unnatural. Some viewed it as a temporary artifact or a mathematical trick, rather than a true description of nature. Even Planck believed classical physics would eventually be restored, and that quantization was just a shortcut. However, the overwhelming accuracy of his formula could not be ignored. To truly appreciate why Planck's solution was so revolutionary, we must understand what he achieved at a deeper level. He resolved a contradiction between theory and experiment that had threatened to undermine the confidence in classical physics. By assuming energy is quantized, he reconciled the behavior of Blackbody radiation with the laws of thermodynamics and statistical mechanics. This resolution was so compelling that it forced the entire scientific community to accept the idea that energy quantization might be a fundamental feature of nature. Eventually, other physicists realized that Planck's proposal was not merely an ad hoc solution. It pointed to a deeper truth. Einstein extended the idea to light itself, suggesting that light consists of quanta, or photons. This bold extension explained puzzling phenomena like the photoelectric effect. Einstein's work built directly on Planck's discovery, showing that quantization was not limited to energy in oscillators, but was an underlying property of electromagnetic radiation. What is remarkable about Planck's solution is that it did not merely solve a technical problem. It exposed an entirely new layer of physical reality. Before Planck, the universe was seen as continuous. After Planck, scientists began to see that the universe might be fundamentally discrete at its deepest levels. The Blackbody radiation problem became the doorway through which the quantum world entered science. Another dimension of this discovery lies in its implications for thermodynamics and entropy. Planck used statistical reasoning to calculate how energy is distributed among oscillators. In doing so, he drew upon Ludwig Boltzmann's ideas about the statistical nature of entropy, an approach that many physicists had resisted. Planck's acceptance of these ideas, combined with his quantization principle, created a new theoretical foundation that challenged classical determinism. Physics moved from a strictly mechanical interpretation of nature to a probabilistic one, foreshadowing the full development of quantum mechanics. The significance of solving the Blackbody problem goes beyond physics. It signaled a shift in how scientists approach unexplained phenomena. The classical view assumed that all physical quantities were smooth and continuous. When this assumption failed to describe Blackbody radiation, Planck broke away from tradition and introduced a concept that was previously unthinkable. This method, challenging fundamental assumptions rather than modifying existing equations, is now a standard approach in modern theoretical physics. Planck's solution fits beautifully into the grand narrative of scientific revolutions. Like Copernicus shifting Earth from the center of the universe or Darwin proposing evolution, Planck's solution transformed the foundations of understanding. His discovery showed that solving a seemingly small theoretical problem could have massive implications for all of science. The impact of the Blackbody solution extends even into modern technology. Many of the devices we use today, thermal cameras, light sensors, infrared detectors, lasers, and even the LED in smartphones, depend on an understanding of thermal radiation that is only possible because of Planck's discovery. Furthermore, the concept of energy quantization underlies quantum physics, which in turn supports technologies like semiconductors, computer chips, MRI machines, and quantum computers. Planck's work also led to the concept of quantized harmonic oscillators, which became the centerpiece of quantum mechanics. These oscillators appear in nearly every branch of physics, from molecular vibrations to the structure of atoms and the behavior of fields in quantum field theory. It all began with the Blackbody problem and Planck's willingness to question classical assumptions. The solution to the Blackbody radiation problem was not simply a single discovery, but the spark that ignited the quantum revolution. Classical physics, though powerful, was shown to be incomplete. Nature's true behavior demanded new principles, new mathematics, and new interpretations. Planck provided the first glimpse of this new universe, and his solution to the Blackbody problem remains one of the most important achievements in all of physics. Continuing from the previous discussion, Planck's resolution of the Blackbody radiation problem not only solved an immediate theoretical puzzle, but also fundamentally changed the way scientists thought about energy, matter, and the interactions between them. By introducing the concept of quantized energy, he created a framework that could explain phenomena that had seemed impossible under classical physics. Before Planck, the prevailing assumption was that energy was continuous. Any amount of energy could be divided into smaller parts indefinitely. Classical mechanics and Maxwell's electromagnetic theory relied on this continuity, and it worked perfectly for many macroscopic phenomena. But Blackbody radiation revealed that this assumption broke down at microscopic scales. Planck's genius lay in recognizing that solving the Blackbody problem required abandoning the idea of continuity, no matter how uncomfortable it might be for physicists of the time. The mathematical formulation Planck introduced was deceptively simple. Energy could only exist in discrete amounts proportional to frequency, expressed as E equals h nu E equals h backslash nu E equals h nu. Here, hh, Planck's constant, became the central quantity determining the size of these energy packets. The equation allowed Planck to fit the experimental data exactly, bridging the gap between theory and observation for all frequencies of emitted radiation. The elegance of the formula lay in its universality. It applied to any blackbody, at any temperature, and across the full electromagnetic spectrum. Once Planck published his results in 1900, the scientific community began to recognize the profound implications. The ultraviolet catastrophe, which had plagued physicists for decades, was gone. The previously unexplainable drop-off in energy at high frequencies made sense, and the entire emission spectrum could be accurately described. This was not just a numerical fit, it was a conceptual breakthrough. The notion that energy itself was quantized challenged every classical assumption about the smoothness of natural phenomena and hinted at a deeper underlying structure to the physical world. The reaction from the physics community was initially mixed. Many were skeptical, seeing Planck's quantization as a mathematical trick rather than a reflection of physical reality. Planck himself was cautious and reluctant to claim that quanta were real. He viewed them as a convenient device to make calculations work. However, the power of the theory was undeniable. Over time, experimental evidence accumulated, and other physicists began extending Planck's ideas. Albert Einstein's work on the photoelectric effect in 1905, which directly applied the concept of quanta to light itself, confirmed the physical reality of energy packets. This validation cemented Planck's solution to the Blackbody problem as not just a fix for a specific puzzle, but as the first concrete step into the new realm of quantum physics. Planck's solution also had profound implications for thermodynamics and statistical mechanics. By treating energy as quantized, Planck was able to reconcile the principles of entropy and energy distribution in ways that classical physics could not. His work showed that the microscopic behavior of atoms and oscillators could explain macroscopic properties like temperature and radiation in a consistent and accurate manner. This statistical perspective, combined with the quantization principle, laid the groundwork for the entire field of quantum statistics and paved the way for later developments such as Bohr, Einstein, statistics, and Fermi, Dirac statistics. Another remarkable aspect of Planck's resolution is its predictive power. The Blackbody radiation formula was not just descriptive. It could predict the behavior of systems under conditions that had not yet been measured. Scientists could calculate the spectral distribution for extreme temperatures, and experiments consistently confirmed Planck's predictions. This predictive success strengthened the credibility of quantum ideas and demonstrated that quantization was not an ad hoc hypothesis, but a fundamental principle of nature. The solution of the Blackbody problem also transformed the role of theory in physics. For centuries, theory often followed experiment, attempting to explain observed phenomena. Planck's approach demonstrated the power of theoretical innovation. By proposing a bold and unconventional idea, he could guide understanding even before experimental confirmation. This approach became a hallmark of modern physics, where theoretical insight often precedes and predicts experimental discoveries. Technologically, the implications of Planck's solution are immense. The understanding of Blackbody radiation underpins technologies that rely on the emission and absorption of thermal energy. Infrared imaging, for instance, depends on quantifying radiation accurately. Lasers and LED operate based on principles of energy quantization that trace directly back to Planck's work. Even modern electronics, which rely on the behavior of semiconductors and electron transitions, would be impossible without the foundational understanding provided by his solution. Philosophically, the resolution of the Blackbody radiation problem challenged the deterministic world, that classical physics had supported for centuries. If energy is quantized, then at microscopic scales, nature is inherently discontinuous and probabilistic. This insight eventually led to Heisenberg's uncertainty principle and the broader probabilistic interpretation of quantum mechanics, which revolutionized our understanding of reality itself. Finally, Planck's solution illustrates the interplay between theory and experiment in scientific progress. The Blackbody problem was a stubborn experimental fact that resisted explanation. Classical physics, though elegant and successful in many domains, could not account for it. Planck's willingness to challenge the foundations of classical thinking, combined with rigorous mathematical reasoning, provided the key to unlocking a new understanding of the universe. His solution did not merely patch a hole in existing knowledge. It opened an entirely new chapter in physics, one that continues to shape both theoretical and applied science today. In conclusion, by solving the Blackbody radiation problem, Max Planck did more than resolve a perplexing anomaly. He revealed the discrete nature of energy, established the principle of quantization, and created the first stepping stone toward quantum mechanics. This achievement bridged the gap between theory and observation, resolved the ultraviolet catastrophe, and provided a foundation for generations of physicists to explore the quantum world. Planck's work exemplifies the power of bold, innovative thinking in science, and reminds us that profound discoveries often emerge from the courage to challenge established assumptions. The statement quantum theory began in 1900 with Planck's revolutionary equation E equals h nu E equals h backslash nu E equals h nu, refers to one of the most pivotal moments in the history of physics. To understand why this single equation marked the birth of quantum theory, it is essential to explore both its scientific context and its profound implications for our understanding of nature. At the turn of the 20th century, physics was dominated by classical mechanics and electromagnetic theory. Classical physics, developed over centuries through the work of Newton, Maxwell, and others, treated energy as continuous and predictable. Heat, light, and motion were thought to vary smoothly. A small change in energy could always be divided into even smaller increments. This framework had proven enormously successful in explaining everything from planetary motion to the behavior of gases. Yet, despite its successes, classical physics faced a serious problem that threatened to undermine its authority: the Blackbody radiation problem. Experiments showed that objects emitted radiation in ways classical theory could not predict. Specifically, classical formulas predicted that the energy radiated at high frequencies should become infinite, a nonsensical outcome known as the ultraviolet catastrophe. This contradiction revealed a fundamental flaw in the understanding of energy and radiation. Max Planck, a German physicist and theoretical thinker, approached this problem with meticulous attention to both experimental results and mathematical consistency. He sought an equation that could match the observed spectrum of Blackbody radiation, which described how objects emit energy across different frequencies at a given temperature. Classical equations worked well at low frequencies, but failed dramatically at high frequencies. Planck realized that the solution required a radical departure from classical assumptions. In December 1900, Planck proposed a bold hypothesis: energy is not continuous, as classical physics assumed, but is emitted or absorbed in discrete units. These units, which he called quanta, are proportional to the frequency of the radiation. Mathematically, he expressed this relationship as E equals h nu E equals h backslash nu E equals h nu, where E is the energy of a single quantum, nu backslash none, U nu is the frequency of the electromagnetic wave, and HHH is a constant now, known as Planck's constant. This simple looking formula had extraordinary implications. By introducing quantization, Planck resolved the ultraviolet catastrophe. The predicted energy distribution now matched experimental observations across all frequencies, both low and high, for Blackbody radiation. Planck's constant HHH is extremely small 626 times 10 minus 3, 146, 626 times 10 minus 34 626 times 10 minus 34 joule seconds, which explains why energy appears continuous in everyday life. At macroscopic scales, the jumps between energy levels are imperceptible, giving the illusion of smoothness. However, at the atomic and subatomic scales, the discreteness of energy becomes significant, and E equals h nu E equals h backslash nu E equals h nu governs the interactions of particles and radiation. The introduction of this constant not only solved a specific problem, but also established a new fundamental unit of measurement for quantum phenomena. The revolutionary nature of Planck's equation lies not only in its ability to match experimental data, but also in its conceptual implications. Prior to Planck, the prevailing view of energy was entirely analog. It could take any value within a continuous range. Planck's quantization challenged this assumption and suggested that nature, at its most fundamental level, operates in discrete steps. This was an entirely new way of thinking, one that would eventually lead to the full development of quantum mechanics, a framework that describes the behavior of particles at atomic and subatomic scales. The impact of E equals h nu E equals h backslash nu E equals h nu extends far beyond the Blackbody problem. It laid the groundwork for many subsequent breakthroughs in physics. In 1905, Albert Einstein used Planck's concept of quanta to explain the photoelectric effect, demonstrating that light itself can behave as a stream of particles, or photons, each carrying energy E equals h nu E equals h backslash nu E equals h nu. This insight provided critical evidence that energy quantization was a fundamental property of nature, not merely a mathematical trick. Later, Niels Bohr applied the principle of quantized energy to his model of the hydrogen atom, explaining why electrons occupy discrete energy levels and why atoms emit light at specific spectral lines. Schrödinger, Heisenberg, and Dirac expanded these ideas into the comprehensive framework of quantum mechanics, all of which rests on the initial concept of quantized energy introduced by Planck. Moreover, Planck's equation fundamentally changed our understanding of the relationship between energy and frequency. In classical wave theory, energy was proportional to the square of the amplitude of the wave, but Planck's relation established a direct proportionality between energy and frequency. This connection provided a new lens through which to view interactions of light and matter. The principle that energy comes in discrete packets of magnitude h, nu backslash none, u became central to understanding phenomena such as atomic transitions, radiation emission and absorption, and even the behavior of electrons in solids. The introduction of E equals h nu E equals h backslash nu E equals h nu also initiated a paradigm shift in how physicists approached problems. Before this discovery, it was assumed that all physical laws could be understood in a continuous, deterministic framework. Planck's work suggested that at microscopic scales, energy and matter might behave probabilistically, opening the door to a more flexible and nuanced understanding of the natural world. This probabilistic perspective would later become a cornerstone of quantum theory, fundamentally altering our notions of causality, measurement, and reality itself. It is important to note that Planck did not initially claim that quanta represented physical reality. He introduced them as a mathematical tool to make the equations fit the experimental data. Yet the mathematical success of E equals h nu E equals h backslash nu E equals h nu was so compelling that subsequent work demonstrated its physical validity. The very small value of Planck's constant ensures that energy quantization is subtle at everyday scales, which is why the classical world U appears sufficient in daily experience. At atomic scales, however, this quantization dictates the behavior of electrons, photons, and atoms, shaping the microscopic architecture of the universe. In addition, Planck's equation has had a lasting technological impact. Understanding energy quantization allows scientists to manipulate light and matter in ways that were previously impossible. Lasers, LEDs, solar cells, and even the principles behind modern electronics and quantum computing depend on the foundational concept expressed in E equals h nu E equals h backslash nu E equals h nu. Each of these technologies relies on controlling energy exchanges at the quantum level, which is only possible because of the discrete nature of energy that Planck first proposed. To summarize, the equation E equals h nu E equals h backslash nu E equals h nu represents more than just a solution to the Blackbody radiation problem. It marks the birth of quantum theory, introducing the revolutionary idea that energy is quantized. This single relation transformed physics, challenging classical assumptions, guiding the development of quantum mechanics, and laying the foundation for modern technology. The insight embedded in this equation that energy is discrete, not continuous, remains one of the most profound shifts in scientific thought, influencing both our understanding of the universe and the technologies that define human civilization today. In essence, quantum theory begins with Planck's insight because it redefined the basic building blocks of reality. Every photon, every electron transition, every quantum interaction can trace its theoretical origin back to this equation. E equals h nu E equals h backslash nu E equals h nu was the spark that ignited the quantum revolution, forever changing how we understand the universe, from the tiniest particles to the largest cosmic structures. It is a simple formula with consequences that are anything but simple, a testament to the power of a single bold idea to reshape all of science. The statement Planck's constant hhh became one of the most important numbers in modern physics, reflects the immense significance of a single physical constant introduced by Max Planck in 1900. This tiny number, seemingly abstract at first glance, has become a cornerstone of our understanding of the universe, bridging theory, experiment, and the technological innovations of the modern world. To appreciate why Planck's constant holds such a pivotal place in physics, we need to explore its origins, implications, and applications in both the microscopic and macroscopic realms. Planck's constant first appeared as a part of Max Planck's solution to the Blackbody radiation problem. Classical physics, which treated energy as continuous, failed to explain why objects at high temperatures did not radiate infinite amounts of energy at ultraviolet frequencies. In a revolutionary move, Planck proposed that energy is quantized. It is emitted or absorbed in discrete amounts proportional to the frequency of the radiation. This relationship was expressed as E equals h nu E equals h backslash nu E equals h nu, where E is energy, nu backslash nun u is frequency, and hhh is Planck's constant. The constant hhh, therefore, determines the size of these energy packets, known as quanta. Without this constant, the quantization principle would lack scale. hhh gives the theory physical meaning. The value of Planck's constant is extremely small, approximately 626 times 10 minus 346, 6 126 backslash times 10 minus 34 6. 6. 126 times 10 minus 34 joule seconds. Its minuteness explains why energy appears continuous in everyday life. A light bulb, a warm stove, or a heated metal rod emits and absorbs energy so many times per second that the discrete steps are imperceptible at macroscopic scales. However, at atomic and subatomic levels, HHH dictates the fundamental behavior of particles, photons, and electromagnetic waves. In this way, Planck's constant serves as a bridge between the familiar, smooth world we observe and the underlying discrete nature of reality. The introduction of HHH marked a profound shift in the conceptual foundations of physics. For centuries, energy was considered a continuous quantity, flowing smoothly and infinitely divisible. Planck's constant forced scientists to confront a new reality. Nature is granular at its most fundamental level. Energy changes in discrete steps, not in a continuous flow. This realization laid the groundwork for the development of quantum mechanics, one of the most successful and far-reaching theories in all of science. Without Planck's constant, the mathematical formulation of quantization would be meaningless, and the entire edifice of quantum theory would lack its foundation. Planck's constant also appears in many fundamental equations of physics, giving it a central role across a wide range of phenomena. Beyond E equals h nu, E equals h backslash nu, E equals h nu, it is a key component of the Heisenberg uncertainty principle, expressed as delta x delta greater or equal to h 4 pi backslash delta x backslash c at backslash delta p backslash jek backslash frac h 4 backslash pi delta x delta greater or equal to 4 pi. This principle states that the position xxx and momentum ppp of a particle cannot both be known precisely at the same time. Here, HHH determines the scale of inherent quantum uncertainty, fundamentally limiting how precisely we can measure microscopic quantities. In essence, Planck's constant sets the boundary between the deterministic world of classical physics and the probabilistic world of quantum mechanics. In addition, Planck's constant plays a crucial role in the Schrödinger equation, the cornerstone of wave mechanics. The equation describes how the quantum state of a physical system evolves over time. HHH governs the oscillatory behavior of quantum wave functions and determines energy levels, frequencies of radiation, and the spacing of quantized states in atoms and molecules. Without HHH, we could not calculate the energy levels of electrons in atoms, the emission spectra of elements, or the behavior of molecules. Entire fields of chemistry, materials science, and atomic physics rely directly on this constant. Planck's constant also appears in Planck units, a system of natural units that describes fundamental scales of nature, including length, time, mass, and temperature. For example, the Planck length and Planck time incorporate HHH to define the smallest meaningful units of space and time in theoretical physics. These units provide a way to think about the universe at its most fundamental level, such as in theories attempting to unify quantum mechanics with general relativity. This demonstrates that HHH is not just a number for energy calculations. It is a fundamental scale, setting constant that permeates our understanding of space, time, and matter. The practical implications of Planck's constant are equally profound. Many modern technologies depend on its value. Lasers, for instance, operate by stimulating atoms to emit photons at precise energy levels, which are determined by E equals h nu, E equals h backslash nu, E equals h nu. Semiconductors, which power computers, smartphones, and almost all modern electronics rely on the quantized energy levels of electrons, a direct consequence of HHH. Quantum computing, which promises to revolutionize computation, is also built upon principles governed by Planck's constant. Even everyday devices like LED, solar panels, and medical imaging equipment utilize phenomena directly linked to energy quantization. Historically, the introduction of Planck's constant marked a turning point in physics. It signaled the birth of a new era where classical intuitions about energy and matter could no longer fully describe the microscopic world. Planck himself considered it a mathematical device at first, but later work by Einstein, Bohr, and others confirmed that HHH represented a real physical property. It became the first step toward the broader quantum revolution that reshaped our understanding of light, matter, and the fundamental interactions governing the universe. Philosophically, Planck's constant challenges our notions of continuity and determinism. Its presence in the uncertainty principle implies that there is a fundamental limit to knowledge at the microscopic level. Nature is not infinitely divisible, nor is it fully predictable. This realization has profound implications for both science and philosophy, influencing how we think about causality, observation, and the very nature of reality. Planck's constant, therefore, is not only a numerical value, but also a symbol of the conceptual leap from classical to modern physics. In summary, Planck's constant HHH is one of the most important numbers in modern physics because it establishes the scale of energy quanta, links the microscopic and macroscopic worlds, and underpins the entire structure of quantum mechanics. It appears in fundamental laws, determines the behavior of particles and waves, sets natural limits on measurement, and guides technological innovations that shape our daily lives. From the tiniest atom to the largest quantum computer, Planck's constant continues to define the way we understand and interact with the universe. In essence, HHH is more than just a number. It is a key to the quantum universe, a bridge between theory and experiment, and a foundational element of modern science that continues to illuminate principles underlying reality. Its introduction marked the beginning of a scientific revolution, one whose influence remains as profound today as it was over a century ago. The statement his work opened the door for scientists like Einstein, Bohr, Schrödinger, and Heisenberg highlights the profound influence of Max Planck's pioneering discovery on the development of modern physics. Planck's introduction of quantized energy in 1900 marked the beginning of a scientific revolution. It not only solved the immediate problem of blackbody radiation, but also created a conceptual framework upon which later generations of physicists built the entire edifice of quantum mechanics. To understand the magnitude of this influence, it is important to trace how Planck's ideas inspired the monumental contributions of Albert Einstein, Niels Bohr, Erwin Schrödinger, Werner Heisenberg, and other leading minds of the 20th century. Planck's discovery of energy quanta challenged classical physics by introducing the idea that energy is not continuous, but comes in discrete packets proportional to frequency, expressed as E equals h nu E equals h backslash nu E equals h nu. This fundamental departure from classical thought provided a new lens through which the microscopic world could be examined. Although Planck initially regarded his concept as a mathematical tool rather than a physical reality, the success of his formula in explaining blackbody radiation forced other scientists to reconsider the nature of light, matter, and energy. It was this conceptual leap that laid the groundwork for the next generation of physicists to explore a new, previously unimaginable universe governed by quantization. Albert Einstein was among the first to extend Planck's ideas. In 1905, in his explanation of the photoelectric effect, Einstein proposed that light itself is quantized, consisting of discrete particles called photons, each carrying energy E equals h nu E equals h backslash nu E equals h nu. This insight provided strong evidence that Planck's quanta were not merely a convenient mathematical device, but reflected a fundamental property of nature. Einstein's work demonstrated that light exhibited both wave-like and particle-like behavior, a concept that would become central to quantum theory. By applying Planck's idea to a new context, Einstein helped establish the principle of wave-particle duality, profoundly influencing the trajectory of 20th century physics. Niels Bohr built directly on Planck's concept when developing his model of the atom in 1913. Bohr faced a critical challenge. Classical physics could not explain the stability of atoms or the discrete spectral lines observed in hydrogen. Using the idea of quantized energy, Bohr proposed that electrons orbit the nucleus in specific allowed energy levels and can only transition between these levels by absorbing or emitting discrete quanta of energy. This model successfully explained atomic spectra and validated the principle of quantization in a new domain. Planck's constant hh was central to Bohr's calculations, determining the size of energy jumps between electron levels. Without Planck's discovery, Bohr's revolutionary atomic model would not have been possible. Erwin Schrödinger, working in the 1920s, further expanded Planck's legacy through wave mechanics. Schrödinger formulated the Schrödinger equation, which describes how quantum systems evolve over time. This equation uses Planck's constant to relate the energy of a system to its wave-like properties, showing that electrons and other particles exhibit behaviors characteristic of both waves and particles. Schrödinger's work transformed the understanding of atomic and molecular systems, explaining chemical bonding, energy levels, and molecular vibrations with unprecedented accuracy. The concept of quantized energy, rooted in Planck's original work, underpinned the very structure of Schrödinger's formulation. At the same time, Werner Heisenberg developed matrix mechanics, an alternative formulation of quantum mechanics that also relied on Planck's constant. Heisenberg's uncertainty principle, formulated in 1927, mathematically expresses a fundamental limit to the precision with which certain pairs of physical properties, such as position and momentum, can be known simultaneously. The constant hh determines the scale of this uncertainty, revealing that indeterminacy is intrinsic to nature at the quantum level. Without Planck's quantization principle and his constant, Heisenberg could not have formulated the uncertainty principle, which has since become a cornerstone of modern quantum theory. Beyond these four giants, Planck's work influenced countless other physicists, from Wolfgang Pauli, who developed the exclusion principle, to Paul Dirac, who unified quantum mechanics with special relativity. The quantization principle became a fundamental feature of all quantum theories, guiding research on atomic structure, particle physics, and field theory. The conceptual breakthrough Planck achieved introducing discrete energy quanta acted as a catalyst, inspiring these scientists to explore phenomena that classical physics could not explain, such as tunneling, superposition, and entanglement. Planck's influence extends not only to theoretical advances, but also to experimental discoveries. By providing a quantitative measure for energy packets through his constant hh, he enabled precise calculations that experimental physicists could test in laboratories. This symbiotic relationship between theory and experiment, initiated by Planck, accelerated the pace of discovery in the early 20th century. Every major advancement in atomic, molecular, and solid-state physics can trace a conceptual lineage back to Planck's quantization principle. Moreover, Planck's work reshaped the philosophy of science itself. Classical physics treated nature as continuous, deterministic, and predictable. The quantization of energy introduced by Planck suggested that at the microscopic level, nature is inherently discrete and probabilistic. This paradigm shift encouraged scientists to question assumptions that had seemed self-evident for centuries. By opening the door to a probabilistic, quantized perspective, Planck allowed Einstein, Bohr, Schrödinger, Heisenberg, and their contemporaries to build a conceptual framework that would revolutionize the understanding of reality. The broader impact of Planck's discovery is evident in modern technologies. The principles underlying semiconductors, lasers, magnetic resonance imaging, and quantum computing all rely on the quantization of energy. Each of these technologies, which define our contemporary world, can be traced back to Planck's bold insight into energy quanta. By providing a fundamental understanding of the microscopic world, Planck empowered subsequent scientists to harness quantum phenomena for practical applications that were unimaginable in his time. In essence, Planck's work created the fertile ground upon which the quantum revolution grew. Without his introduction of energy quanta and the constant HHH, the conceptual leaps made by Einstein, Bohr, Schrödinger, Heisenberg, and others would not have been possible. Planck's discovery provided the first glimpse into a universe governed by quantization, inspiring generations of physicists to explore, expand, and formalize the principles that now define modern physics. His work demonstrates how a single insight rooted in careful observation, mathematical reasoning, and bold creativity can reshape the course of science, opening doors to discoveries that transform both theory and technology. Planck's influence thus transcends individual discoveries. He did not merely solve a problem of Blackbody radiation. He revealed a hidden structure of reality, laying the foundation for an entirely new physics. His work sparked a cascade of intellectual breakthroughs, setting the stage for a century of profound scientific achievements. Einstein's photons, Bohr's quantized orbits, Schrödinger's wave functions, and Heisenberg's uncertainty principle all owe their existence, conceptually and mathematically, to Planck's revolutionary insight. By opening this door, Planck became not just a pioneer of quantum theory, but the starting point of a scientific revolution that continues to shape the way we understand the universe today. The statement "quantum theory transformed our understanding of atoms, light, and the universe" captures the profound impact of quantum physics on the way we perceive reality. Quantum theory, which began with Max Planck's introduction of energy quanta in 1900, completely overturned the classical view of nature, revealing a world that behaves in ways that defy intuition, yet govern everything from the tiniest particles to the largest cosmic structures. To understand this transformation, it is essential to examine its influence on three interrelated domains: the structure and behavior of atoms, the nature of light, and the fundamental principles governing the universe. Before the advent of quantum theory, the atom was largely a mystery. Classical physics, based on Newtonian mechanics and Maxwellian electromagnetism, could not explain why atoms were stable or why they emitted light at specific frequencies. The Rutherford model, proposed in 1911, described atoms as having a dense nucleus surrounded by orbiting electrons. However, according to classical theory, the electrons should continuously radiate energy as they orbit the nucleus, causing the atom to collapse. This contradiction between theory and observation highlighted the limitations of classical physics and set the stage for the revolutionary insights of quantum mechanics. Max Planck's concept of energy quantization provided the first hint that the behavior of microscopic particles is fundamentally different from that predicted by classical laws. Niels Bohr expanded on this idea in 1913 with his model of the hydrogen atom. Bohr proposed that electrons occupy discrete energy levels and can only move between these levels by absorbing or emitting specific quanta of energy, given by E equals h nu, E equals h backslash nu, E equals h nu. This explained why atoms emit light in discrete spectral lines rather than a continuous spectrum, and solved the problem of atomic stability. The Bohr model was the first framework that successfully merged quantization with atomic structure, providing a clear picture of the microscopic world. Erwin Schrödinger and Werner Heisenberg further developed the quantum framework, offering complementary descriptions of atomic systems. Schrödinger introduced wave mechanics, portraying electrons as wave-like entities whose probabilities of being in certain locations are described by a mathematical function called the wave function. Heisenberg, on the other hand, developed matrix mechanics and the uncertainty principle, showing that certain pairs of properties, such as position and momentum, cannot both be precisely known. Together, these approaches transformed our understanding of atoms from static, classical particles to dynamic, probabilistic entities governed by quantized energy levels and wave-particle duality. Quantum theory also revolutionized our understanding of light. Before Planck, light was understood solely as a wave, as described by classical electromagnetic theory. However, experiments such as the photoelectric effect demonstrated that light can also behave as a particle, with energy carried in discrete quanta called photons. Albert Einstein, building on Planck's work, proposed that each photon carries energy E equals h nu, E equals h backslash nu, E equals h nu, explaining why light of a certain frequency, regardless of intensity, can eject electrons from a metal surface. This wave-particle duality challenged centuries of classical assumptions and introduced a new perspective, light, and by extension, all matter exhibits both wave-like and particle-like properties, depending on how it is observed. The implications of quantum theory extend beyond atoms and light to the broader universe. Quantum mechanics introduced fundamental limits on measurement, probability, and determinism. For example, the Heisenberg uncertainty principle implies that the behavior of particles cannot be predicted with absolute certainty. The universe at its core is probabilistic rather than strictly deterministic. This realization transformed the philosophical foundations of science, challenging long-held beliefs about causality and the predictability of nature. It suggested that at microscopic scales, nature operates according to rules that are fundamentally different from those governing macroscopic objects, yet these rules give rise to the structure and behavior of all matter in the universe. Quantum theory also explains a wide range of physical phenomena that classical physics could not, from the stability of matter to the behavior of solids, liquids, and gases. The Pauli exclusion principle, derived from quantum mechanics, explains why electrons occupy distinct orbitals and why matter has structure, volume, and rigidity. Quantum mechanics also governs chemical reactions, molecular bonding, and the behavior of light in materials. These principles are foundational to modern chemistry, materials science, and nanotechnology. Without quantum theory, the behavior of the world at the microscopic level would remain a mystery. The impact of quantum theory extends even to cosmology and our understanding of the universe. Quantum mechanics underpins theories of stellar evolution, nuclear fusion in stars, and the behavior of matter under extreme conditions such as in neutron stars and black holes. Quantum field theory, which combines quantum mechanics with special relativity, provides the framework for understanding fundamental forces and particles. In addition, concepts such as quantum entanglement and superposition, initially counterintuitive, have led to cutting-edge research in quantum computing, communication, and cryptography, demonstrating the practical implications of quantum principles on a cosmic and technological scale. Technologically, the insights of quantum theory have transformed human life. Devices such as lasers, semiconductors, MRI machines, LEDs, and solar cells all rely on the principles of quantization, wave, particle duality, and energy levels introduced by quantum mechanics. Quantum theory not only explains why these technologies work, but also guides the development of future innovations, such as quantum computers, which promise to revolutionize computation by exploiting superposition and entanglement. Every aspect of modern electronics, communications, and imaging is profoundly influenced by the understanding of atoms and light provided by quantum theory. Philosophically, quantum theory has reshaped our world. It challenges the notion that reality is fully deterministic and that the universe can be understood in purely classical terms. Instead, quantum mechanics reveals a universe in which probabilities, uncertainty, and discrete phenomena govern the fundamental behavior of matter and energy. This conceptual shift has implications beyond physics, influencing philosophy, information theory, and even our understanding of consciousness and the limits of human knowledge. In conclusion, quantum theory transformed our understanding of atoms, light, and the universe by revealing the discrete, probabilistic, and dual nature of fundamental entities. Planck's introduction of energy quanta initiated a revolution that was extended by Einstein's photon theory, Bohr's quantized atomic model, Schrödinger's wave mechanics, and Heisenberg's matrix mechanics and uncertainty principle. Together, these developments redefined the microscopic world, explained the behavior of light, and reshaped the conceptual and practical understanding of the universe. Quantum theory provides the foundation for modern physics, chemistry, and technology, offering insights into the structure of matter, the behavior of light, and the fundamental laws that govern the cosmos. Its influence permeates both scientific thought and technological innovation, making it one of the most profound and transformative achievements in human history. The statement, "Today's technologies, lasers, computers, smartphones," trace back to Planck's discovery, highlights the enormous, practical impact of Max Planck's pioneering work on energy quantization and the birth of quantum theory. While Planck's original research was theoretical and concerned with Blackbody radiation, the principles he uncovered laid the foundation for an entire technological revolution. The devices and systems that define modern life, from everyday electronics to advanced scientific instruments, are deeply rooted in the concepts he introduced, demonstrating how a fundamental scientific discovery can reshape society in profound and unexpected ways. Planck's key contribution was the idea that energy is quantized. He proposed that energy is not continuous, as classical physics had assumed, but comes in discrete packets, or quanta, of size E equals h nu, E equals h backslash nu E equals h nu, where HHH is Planck's constant and nu backslash nun, U is frequency. This principle initially solved the Blackbody radiation problem, explaining why hot objects emit radiation in a way that classical physics could not. While this may have seemed like a purely abstract solution at the time, the notion that energy is quantized became the cornerstone of quantum mechanics. Without this fundamental concept, the understanding of electrons, atoms, and photons, the building blocks of modern technology, would have been impossible. One of the most visible technological applications of Planck's discovery is the laser. Lasers, which produce highly focused and coherent beams of light, rely on the principles of quantum mechanics, particularly the quantization of energy levels in atoms and molecules. When electrons in atoms absorb energy, they jump to higher energy levels, and when they return to lower levels, they emit photons of specific energies. The precision of this emission, governed by Planck's constant, allows lasers to produce light of a very specific wavelength and intensity. Lasers are now ubiquitous in daily life, powering optical communication systems, barcode scanners, CD and DVD players, surgical instruments, and even advanced manufacturing techniques. Without Planck's insight into energy quanta, the controlled emission of photons that makes lasers possible would remain unexplained. Computers, both classical and emerging quantum versions, also trace their roots to Planck's work. The operation of semiconductors, the foundation of modern electronics, depends on the behavior of electrons in materials at discrete energy levels. Transistors, which are the building blocks of microchips, control the flow of electrons by exploiting quantized energy bands. Understanding these bands requires knowledge of quantum mechanics, which originates from Planck's discovery. Every smartphone, laptop, and data center relies on semiconductor technology, which would be unintelligible without the principles of energy quantization and electron behavior first elucidated by Planck. Moreover, the emerging field of quantum computing directly leverages Planck's concepts, using superposition and entanglement to encode and process information in ways impossible for classical computers. Smartphones, which combine multiple technologies, also owe their functionality to quantum mechanics. The screens use LED, which emit light through the recombination of electrons and holes in semiconductors. The behavior of electrons in these materials is governed by quantized energy states. The communication capabilities Wi-Fi, cellular networks, and Bluetooth depend on controlled electromagnetic waves, whose interactions with antennas and circuits follow quantum principles. Even the sensors in smartphones, such as cameras and gyroscopes, operate through mechanisms influenced by quantum behavior. Planck's original insight that energy is quantized underpins the operation of these everyday devices, even though users are rarely aware of the quantum principles at work. Planck's discovery also paved the way for medical and scientific technologies. Magnetic resonance imaging (MRI), for example, relies on the quantum behavior of atomic nuclei in a magnetic field. The spin states of nuclei and the transitions between them are quantized, governed by principles that stem from Planck's work. Lasers, as mentioned earlier, are used in surgical procedures, optical diagnostics, and even in the development of advanced imaging techniques. These technologies not only enhance human life, but also demonstrate the practical applications of quantum theory in solving real-world problems. In addition, modern communication infrastructure is deeply influenced by Planck's discovery. Fiber optic networks, which transmit data as pulses of light, rely on the quantized interaction of photons with matter to minimize loss and maximize efficiency. Photodetectors, modulators, and amplifiers, all essential for high-speed internet and telecommunication systems, operate based on quantum principles. The development of these technologies would have been impossible without the foundational understanding of photons and energy quanta that originated with Planck. Planck's work also influenced the development of electronics in general. Devices such as transistors, diodes, and integrated circuits all rely on the behavior of electrons in quantized energy states. Quantum mechanics explains phenomena such as tunneling, which is critical for flash memory and other semiconductor devices. Without understanding the discrete nature of energy levels and the principles of quantum mechanics, engineers would not have been able to design the components that power computers, smartphones, and other electronic systems. Beyond the immediate devices, Planck's discovery laid the foundation for an entire technological paradigm known as the quantum revolution. Technologies that would have seemed like science fiction a century ago, quantum cryptography, quantum sensors, and quantum computing, are now emerging as feasible innovations. All of these rely on the principles of superposition, entanglement, and discrete energy levels, all of which trace back to the quantization of energy that Planck first introduced. In essence, the modern digital world, with its vast networks, powerful computation, and advanced electronics, is a direct consequence of Planck's theoretical insight. Philosophically, the connection between Planck's discovery and contemporary technology illustrates how pure science can drive technological progress. Planck was initially motivated by the desire to understand blackbody radiation, a problem that seemed abstract and removed from practical concerns. Yet his discovery of energy, quanta, became the foundation for technologies that shape everyday life. This demonstrates that fundamental research, driven by curiosity and the pursuit of knowledge, can have long-term, transformative impacts on society. In conclusion, today's technologies, lasers, computers, smartphones, and much more, are direct beneficiaries of Max Planck's discovery of energy quanta. His introduction of the constant HHH and the concept of quantized energy did more than solve a theoretical physics problem. It established the principles that govern the behavior of electrons, photons, and atoms. These principles form the foundation of semiconductor devices, lasers, communication systems, medical imaging, and emerging quantum technologies. From everyday gadgets to advanced scientific instruments, Planck's discovery underpins the modern technological landscape. By demonstrating that fundamental scientific insights can translate into practical innovations, Planck's work exemplifies the profound and lasting influence of theoretical physics on human civilization